Okay, so in this video, I want to talk about a clever algorithm that uses this array implementation of a heap to build a heap up from scratch when you have n elements already that you maybe have in a list or something. So let's describe this operation called buildHeap that takes n elements as parameters and constructs a priority queue or a heap from them containing exactly those n elements. So the first idea I would think of is just add each element in one at a time. So just call the add method, passing in each element and letting your implementation of the array heap or whatever you're implementing your priority queue with handle moving of values around. Now, remember, regardless of our implementation in practice or worst case, when we have this array implementation, we get this maybe in practice theta of 1 runtime for that add, but that worst case log n. Now, if you think about what's happening in the worst case runtime, not the in practice case, the worst case, each call to this would take something like logarithmic time, and you're going to call it n times. So this is going to be something like n log n. Now, this isn't quite that simple because each time through the loop, you're kind of changing the size a bit, right? But this intuition is good enough. This n log n intuition is good enough, and it turns out to be a good bound in reality, but it's a little more complex to actually prove this. Now, the reason is, and even though most of the time you're not going to be hitting this worst case log n on each of those calls, because a lot of those calls are going to be going on an empty tree, this intuition is kind of the right thing. So there's a really non-obvious algorithm here that uses this array structure in a very, very clever way. So the question here is, can we do better? Now, to think about why this second idea is going to help is that n addition strategy that we just described, every time we do an addition, we're adding a node at the bottom, and it might need to percolate all the way up. So the idea is, well, is there a better way of structuring the data originally so that we don't have to do as much percolating up? So here's the totally not obvious idea. Put everything in an array and then percolate things down until we fix the heap invariant. This algorithm is called Floyd's algorithm, and the intuition here is that this could be faster, assuming that there's something clever we can do with this percolate down. Now, think about the reason this is going to work in practice, and I'll show you an example of how we actually do this, is because most of the nodes in the tree are in the bottom levels, right? I said there's this doubling trick. Each time you go down a level, there's twice as many nodes at the next level. So it's going to be the case that the majority of the nodes are at the bottom, near the bottom. And when you percolate things down from the bottom, there's not very far down to go. So the intuition here is that most of the nodes won't have to travel very far. Let me give you a concrete example of what this algorithm is doing and why this intuition is going to help us. So this algorithm is called Floyd's algorithm. It takes an array of values or a list of values and turns them into a binary heap, assuming an array implementation. So suppose I had this list of values here, 12, 5, 11, and so on. Our original approach was just add each one individually and then do a percolate up for each one. But the idea here is just simply start by sticking all of the values in the array in the order that we received them. Just put them in the array. This is not a heap because it's not going to have our heap invariant, but we're going to fix that. So remember, whenever you have this array implementation, it's really, really important to think about the tree version of this. What does this array represent? Because there's not this really clean mapping of kind of this picture of the array in your head to what this tree should look like. So it's always good to maybe draw out a picture of what does this array represent in tree form so that I can think about what these operations are doing. So then, once we've added all the values in the array, now we're going to go through and try to fix it. Make sure that the heap invariant is satisfied. So the idea is we start at the last index, so go to the very end, and we're going to start percolating down and iterating backwards while we do so. So we start at the 6, and one of the important things here is that all of the leaf nodes, they never needed to be percolated down because they have no children underneath them. They're not violating the heap invariant because they have no children. So we can kind of go ahead here and just skip essentially all the leaf nodes. You don't necessarily need to program different logic for that. You just loop through and be like, oh, there's nothing for me to check. I just move on. So we just keep moving back. Now, so kind of this level 4 of the node, this 4th level here, that's kind of all done. They're in the right place. They haven't violated any invariant, so that's great. Then we just keep moving backwards. Now we're going to start percolating level 3. The 9 and the 2, totally fine. They don't violate the heap invariant. But then we get to this 10. And we see, well, on each iteration here, I'm basically just checking if there are children, are they less than me? So this 10 has a child that's less than it. Oh, I should quickly mention, in this picture I'm showing you, I'm starting the array indices at 0. Remember, back from the last video, you could also start them at 1. It just changes your math slightly, but the algorithm is exactly the same. But here I'm just starting at 0 for simplicity. So here you can check your left and right child. You have the 15 and the 7 as your children, and that violates the heap invariant because 10 is not less than 7. So what do? We need to percolate it down. So we're going to end up swapping the 7 and 10, and in our mental model, that's like swapping the nodes, but in the implementation, we just swap the values of the indices. This index and that child index, you just swap those values around. Now, we can just keep going. So we say, okay, that 7's in a good place, the 3's in a good place, so let's just keep going kind of to the left, kind of going back up the tree. Notice we're kind of going in this tree because we're going from right to left. We're kind of going from right to left in the tree as well because of how we laid it out in this array. So 3, all good, nothing to percolate down. Then we go to the 11. The 11 we do have to percolate down because it's larger than its children. So we swap it with its smallest child. So we swap it with the 2, which involves swapping them in the places with the array. Then, unfortunately, what we didn't see in the last example is you have to keep percolating that value down until it finds its right spot. So here, we can't just do one swap. We actually have to let the 11 fall all the way down to its right spot in the tree. So we keep doing percolate down until we find the right spot. So the 11 is going to have to swap down again. But now we can just go back to where we left off. Everything's great, and we continue. We percolate the 5 down, and the 5 would have to swap with the 4 below it, but I'm just going to skip that in my animation. And then we kind of get to that last node and percolate that down all the way to wherever its right place is. So now we have this tree. Kind of clever, probably not clear that this is actually faster than that first idea. Now, the intuition for why this is going to be faster is that the majority of the nodes are lower in the tree. And if the node is lower in the tree, you're not going to be swapping it a lot, or you're not going to be percolating it down. So it's going to, that percolate down operation does in the worst case have log n runtime if you're percolating something from the top of the tree all the way down. But most of these nodes are going to have something much, much smaller than the worst case. Half the nodes in the tree have 0 levels to travel because we just start them off at the bottom. They're not violating the invariant. A quarter of the nodes have 1 level to travel because they're just 1 above the leaf nodes. An eighth, 2 levels to travel, all the way up to the logarithmic n height. And so you kind of have this kind of weird geometric sum where much of the work is only doing some constant step, a little less of the work is doing 2 steps and then 3 steps, all the way to that last one. In the worst case, we'll have to go down all log n. And so even though there are these log n levels, and at the top they might be doing this log n work, very few nodes actually have this worst case. Most of them are near this constant time. Now, I have in this next slide here kind of an optional, here's the math to prove this. Notice I tag it as optional. We don't need to worry about this. This uses some slightly more advanced sums than we saw when we talked about the tree method. It's the same idea though, just bounding the sum by some closed form. But you can look through this if you're interested, but we're not interested in it for this quarter. We don't expect you to understand this math. We do want you to understand, in some sense, the English description of why this works. Why this, when you have most of the nodes only going a constant distance, this actually does speed this up. Importantly, I kind of hid this up near the top. This overall runtime ends up being linear. If you do all this math, it ends up being something like big O of n, which is great because we don't need this n log n business. we can just essentially do this in linear time, which is such a clever algorithm for this to build up a heap from n elements without having to do n log n insertions, which is pretty great. Now, one thing I want to mention, kind of now that we've talked about this algorithm, a clever algorithm, and again, a very not obvious algorithm from the get-go of how we could go ahead and build that up. But this maybe gives some motivation for why we like implementing these priority queues, or these heaps in particular, with arrays. Because the math tends to be a little bit simpler in terms of finding indices, and you can do these really complex algorithms, like Floyd's algorithm, in relatively simple steps. So for your project 3, the next project that's coming out today and is due in 2 weeks, you're going to be building a heap. So alongside the hash maps that you're programming in project 2, heaps are one of the most useful data structures to know. And they pop up they're going to pop up, as I mentioned, with the priority queues a lot of times this quarter. And so you'll actually get practice in this assignment, not only kind of implementing this idea so you really understand all the mechanics, but you also get practice with some common design challenges when it comes to implementing classes or doing something with anything complex. You're actually going to be working with multiple data structures together to implement a particular ADT. One thing I'll also mention is that when we've been highlighting this point of invariants. Invariants are so important. And to make this point even a little bit more closer to home in terms of your project, we're actually going to give you what we call an invariant checker. So some of our tests are going to actually check the state of your object and make sure that the invariants we set up hold. This is a very good idea for what we call defensive programming. It essentially lets you stop bugs before they happen, because usually most of your bugs, you probably realized in project 2, was your state got in a place that you didn't expect it would. Maybe a bucket was empty when you didn't think that would be possible. You maybe had an invariant in mind that wasn't actually in your implementation. And these invariant checks will help you ensure that any assumptions you're making are true. So you're going to be implementing a class that has this min priority queue ADT kind of that's trying to implement. So adding, removing the min, peeking at the min. You're going to use this array implementation. Now, we also actually added some extra methods to this ADT that we want you to implement. One of them is called change priority. So given an item, update its priority and change kind of its location internally to work with that, and asking if a particular item is contained in this structure. Now, it's probably not super clear why we're adding these. You can maybe imagine a context where it would be useful to update something when it's in there. But the reason we want to add these is because for your next project, when we're using an application of priority queues, these operations are going to be really helpful. So we want you to implement them now so that we can talk about them when we get to like the next idea of talking about this thing called Dijkstra's algorithm. But we'll get there later. Don't worry about it, but you do need to implement this now. I do want to give you a bit of a tip. One of the things we saw from the mid-quarter assessment was sometimes people felt like it's a little tough to tie what we were talking about a lecture to the project. And so I want to make sure we have this like tip section when a new project comes out to talk about what we're doing in class relates explicitly to the project. So one thing I'll mention is that all of the things we just talked about in terms of the basic array implementation, kind of that reference slide in terms of the indices, kind of the visualization of how to do these algorithms, all of that is going to be really useful. So applying the idea to the actual code. That's in some sense the fundamental challenge of programming. You have an abstract idea of what you're going on. Maybe you got it from lecture and we talked about it in these videos. And then trying to figure out what is the code to write that. That's just not a 373 problem. That is just a coding problem. And so hopefully you're getting a lot of practice with coding stuff. And if you ever get stuck, you should come to office hours. We can talk about coding techniques, help you develop the skills for debugging and things like that. But one thing I want to mention is probably one of the places you're going to struggle the most on this assignment is this change priority function, because it's actually a little tricky to implement. So I wanted to highlight this. So it is going to be totally fine for you to use extra data structures internally to help you implement this change priority. You'll see that the change priority with just our array is going to be a little inefficient. And so we're going to actually want you to maybe make it faster. And that will actually, I'm not going to say probably, will require that you maybe use another data structure internally to help you keep track of some state. This doesn't affect the correctness of the priority queue from the outside, it just affects the runtime to make these operations faster. So you will probably want to use one of Java's built-in collections to help you implement this faster than trying to write your own thing from scratch, even though you technically could do that. So what we recommend when you get to the change priority part is that first just implement it, don't worry about efficiency. Just you have your array implementation, just go through it, figure out how you're going to do that, and then see that you might run into efficiency problems. Then figure out when it comes to change priority, what part is actually slow, and figure out, well, maybe is there another data structure I can use that can help me solve this problem? And so you might want to reflect back on the data structures we've learned so far and figure out, like, is there a tool here that can help me solve this particular task? Again, the backbone of what you're going to be implementing is this array structure for the heap. But you might want another structure on top of that, another structure that you also use to help you answer some slightly different questions that the heap doesn't do very well. I'm going to leave that to you as something you're going to try to figure out. Use the things we've talked about so far and apply that to trying to solve this. But again, I do want to mention, sometimes we have this hesitation, like, do I really need an extra data structure here? Once you get to change priority, you're definitely going to want another data structure. So I hope you enjoy Project 3. It's really, really cool, and make sure you actually understand how all these things relate, this array to the picture of the tree, and I hope you enjoy this project. We have one more video coming up talking about software industry and interviews, and so hopefully you stick around for that so we can show you some extra resources.